My name is Guglielmo Grimaldi, and this is the video abstract for the paper Minimax Surfaces and the Holographic Entropy Cone by Brian White, Matthew Hedrick, Veronica Hubany, and myself. A central question in holography is to understand how the bulk geometry is encoded in the entanglement structure of the boundary state. Geometric states that are dual to classical smooth spacetimes are more constrained than general states in quantum mechanics. The entropies computed by the Ryu-Takeinagi formula are known to obey an infinite set of inequalities. Central to the study of these holographic inequalities is the graph model. By partitioning the bulk slice using all RT surfaces of single and joint parties, one gets a cell decomposition of the slice. To each cell we assign a vertex, and to each pair of vertices that share a part of an RT surface we assign an edge. The weight of this edge will be the area of the portion of the RT surface that it cuts. Then, computing entropies corresponds to finding the mean cut on this graph. An open problem is to understand whether this set of inequalities remains unchanged when moving to the general time-dependent setting, where the HRT formula must be used. Partial progress has been made on this front from multiple directions, but the full structure is yet to be found. One complication is that it's not understood whether a general time-dependent state admits a graph model. As you can see, the HRT surfaces do not lie on a common slice, so a graph that computes entropies through mean cuts is not only unclear how to be covariantly constructed, but it's not obvious that it even exists. In this paper, we attack the problem by using a new formulation of holographic entanglement entropy known as Minimax, which involves finding the maximal area surface on a time-like hypersurface known as timesheet, and then minimizing over the choice of timesheets. The solution to this equation is a Minimax surface lying on a Minimax timesheet. These timesheets are required to be homologous to the domain of dependence of the boundary region. This is a key feature of this prescription. The homology condition, which is usually enforced through a bulk Cauchy slice, here is enforced at the level of the spacetime. In other words, the homology regions are spacetime volumes. We prove multiple properties of Minimax surfaces and their timesheets. Some of these are known results, but others are new. For example, we are able to show that the entanglement wedge is the smallest homology region bounded by Minimax timesheets. We found the Minimax prescription particularly useful because of this new spacetime homology constraint, which has interesting consequences. Just like RT surfaces partition the bulk slice in the static context, here timesheets partition the bulk into spacetime cells. This allows us to construct a spacetime graph model covariantly by assigning vertices to spacetime cells and connecting vertices that share part of a timesheet. This graph model will be equivalent to the RT graph, subject to a crucial property, that the partial HRT surfaces that are contained on the partial timesheets are maximal on the respective partial timesheets. For the previous graph, the property we want to prove reduces to showing that there exists a choice for these two timesheets such that the four partial surfaces are maximal. We provide a proof of this statement in the paper. To construct a graph model for finer boundary subdivisions, we need the above property to hold for configurations of arbitrary many timesheets intersecting. We don't have a proof for this general case. However, we test the validity of the conjecture by studying various configurations of increasing complexity. We were able to show that a cooperating configuration exists for certain classes of surfaces, such as the one shown on the left, but not in others, particularly when three maximally boosted surfaces intersect or come close, as shown on the right. Therefore, the cooperating property remains an open conjecture to be further studied. All in all, the Minimax prescription seems to be a new powerful tool in holography. It provides us with new techniques to prove theorems, as well as new conceptual ideas, like the spacetime homology constraint, that might be crucial in setting up the framework to study the entanglement structure of general holographic states. Thank you.